I don't know if you've heard, but there is a virus that took over most of the world in the past year. I haven't dedicated any episode to COVID yet. First, because research was moving a lot and fast. And second, because modeling COVID is very, very hard. But we know more about it now. So I thought it was a good time to pause and ponder. How does the virus circulate? How can we model it and ultimately defeat it? What are the challenges in doing so? To talk about that, I had the chance to host Michael Osthege and Thomas Vladeck, who both were part of the team who developed the RT-Live model, a Bayesian model to infer the reproductive rate of Covid-19 in the general population. As you will hear, modeling the evolution of this virus is challenging, fascinating, and a perfect fit for Bayesian modeling. It truly is a wonderful example of Bayesian generative modeling. Tom is the managing director of Gradient Metrics, a quantitative market research firm, and a co-founder of Recast, a media mix model for modern brands. Michael is a PhD student in laboratory automation and bioprocess optimization at the Forschungszentrum Jülich in Germany, and a fellow PyMC core developer. As he works a lot on the coming brand new version 4, we'll also take this opportunity to talk about the current developments and where the project is headed. This is Learning Bayesian Statistics, episode 33, recorded May 25, 2021. Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country, and reach a true Bayesian state of mind by visiting learnbayesstats.com. That's learnbayesstats.com. Do you want to support the podcast and unlock exclusive Bayesian swag at the same time? Then you can visit my Patreon page at patreon.com/learnbayesstats. Starting at €3, you can get various benefits like the private MBS Slack channel, early access to special episodes, selecting questions for episodes, or even coming on the show. You'll get more details at patreon.com/learnbayesstats. Thanks a lot, folks. I'm very grateful for any support you can bring me.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations.
What's a Bayesian? Is someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly I'm watching eyes widen, maybe cause my likeness lowers expectations of tight rhyming. How would I know unless I'm rhyming in front of a bunch of blind men dropping placebo-controlled science like I'm Richard Feynman?
Hey folks, I'm proud to say that this episode is brought to you by PepperPie. PepperPie is the reference manager you actually want to use. It integrates seamlessly with Google Docs, and if you use things like Slack, Trello, or Gmail, you're gonna love it. Make sure to listen to the dedicated segment during the show to discover how they make your life easier. By the way, if your company wants to support this podcast, raise its brand awareness, or put its job ads in front of the right people, just get in touch with me and we'll see what we can do together. Michael Osthege, Tom Vladeck, welcome to Learning Bayesian Statistics.
Thanks for having me.
Yeah, thanks for having us.
Yeah, really glad to have you there. I said Michael, but I'm not sure I'll be able to not say Michael during the show. Please excuse me.
No, that's fine.
Yeah, it's like talking in English, then switching to German can be a bit confusing. Okay, so yeah, I'm really glad to have you there and to finally dedicate a whole episode to COVID modeling. Yeah, now that we have had some time to digest all that happened and all that is still happening, I think it's an interesting time now that most of the US and part of Europe are mainly reopening to take a look back and see at what you guys did with the RT-Live model and a bunch of other stuff. But first, as usual, let's start with your background because you both come with different experiences. So I love that. Yeah, so what are your stories, basically? Maybe Tom, if you want to start?
Yeah, sure. So my background, like way back in the day, I studied math in college and then promptly sort of forgot about it. And I had a career in nonprofits and climate change, and then eventually sold out, went to business school here in the US. And then it was at business school that I sort of rediscovered math, statistics, et cetera, through the lens of marketing. So there is this world of marketing. I did not know this before I went into business school that is very, very, very statistics focused. And so it was in business school that I was like, wow, I can be a nerd for a living. I can just do statistics, work with data, write code. And that's a perfectly acceptable way to be in the business world. And I loved it so much that I started a company called Gradient that does basically quantitative market research. So we collect data, build models on top of it. And then I have another company called Recast that does like media mix modeling. And over time, got really into the Bayesian worldview, way of thinking about things, way of approaching problems. And so kept learning, and eventually became pretty proficient at Stan, which is a PyMC3 competitor, but they're very supportive competitor. And we'll get into this, but one of the areas where I spend a lot of time thinking is type of model called a state space model, which is a way of modeling data over time. And it's something I've thought a lot about, and that sort of was my wedge into the RT world. So we can talk more about the origins of the model, but my background is mainly in marketing and statistics, but some of the things that I gained some expertise in have broader applicability and were relevant to this specific problem that we will be discussing soon.
Nice. We will, indeed. I love the fact that you started with math. And then, why did you go into on the business school road? Was it because maybe you didn't find the math teaching that you received, I don't know, concrete enough or something that you could apply right now?
Yeah, well, so, basically I hit a crossroads with my career where I just really needed to do something different. And, it's not uncommon, I think, for people to go to business school basically to get a tabula rasa, to get a clean slate in their career. That's what I did. And the reason that I went into writing code and doing math for a living was that prior to business school, I had been very focused on the industry, for lack of a better word, which was climate change, but not so focused on what I was doing day to day. And then in business school, I was like, well, I really like to think through math problems and I really like to write code. So I want a career that's going to do that. And I was less focused on the industry. And so that's how that transition happened for me.
Okay, I see. Yeah, I can relate to that. Had a bit of the same path, actually. And Michael, now, what about you? How did you end up where you are right now?
Yeah, I think my story is quite different to what we just heard from Tom, because I don't really like math. And I actually studied molecular biotechnology. I always had let's say, affinity for programming, but my primary interest really is biotechnology. And in my bachelor's, I also participated in this. There's this competition. It's called iGEM. It's like the World Championship for Genetic Engineering. And twice, together with a team of 15 people, I participated there. Had a lot of great time in the lab doing experiments, molecular biology. But then at some point, I started having this interest in machine learning and modeling. And I kind of decided to step out of the wet lab, as we say, and continued my master's in systems biology, which is basically mathematical modeling of biological systems, not because I was interested in the math, but because I think that with mathematical modeling, and particularly Bayesian modeling, of course, we can extract a lot more information from biological experiments. So that's how I got into modeling. And now I'm actually doing a PhD in laboratory automation for bioprocess optimization. So I'm kind of sitting at the intersection between programming the robots to run experiments that create data sets, and then modeling these data sets with PyMC3, of course. So yeah, whenever there is something wrong with the data, either myself or my students are at fault. So that's quite good, but it can also be quite exhausting.
Yeah, can guess that. And also if the robots rise up and take over the earth, we have you to blame. So that's good to know.
Oh, I have absolutely no fear of that, because let's just say the software that runs these robots isn't the most reliable. um, so, yeah, we're safe. At least the robots from biotechnology and lab automation, they will not take over.
Unless you put production-ready software like the ones we talk about on this podcast in there, then we are doomed. Like if you put Stan or PyMC and do that, then we are doomed. These softwares are so good.
They never break.
They never break. They don't have any bugs. I mean, it's impressive.
No bugs. Never seen a bug.
The guys writing that are just...
Well, we definitely try to write production-ready software, because when an experiment fails after 2 days in the middle of the night, and the experiment took a few days to prepare, costs $1,000 and takes a week of precious robot time, then we don't end up with a data set. And so no data is bad data. But bad data is also not always the greatest thing.
And you were saying that you were using PyMC3 to model at least some of the models you were working on. So yeah, I'm curious how Bayesian is your work, or most of your models. Do you need the Bayesian structure for that, or are you using more classical machine learning sometime?
Well, the thing with classical machine learning is that it often needs a lot of homogeneous data, but we don't run experiments in the same way over and over again. So we often have very heterogeneous data sets where we try out different things, have different conditions in the experiment and different candidates. And then those classical techniques of machine learning, they don't really apply, because you don't have many options how you can represent this hierarchical and heterogeneous structure of the data in these models. So I think that Bayesian modeling is a really good fit, also because it incorporates uncertainty by design. And uncertainty is really important here, because we often deal with very few data points that are very noisy. So I think it's a great fit, but the field is not very Bayesian yet. So we're trying to change that, of course.
Paper by paper?
Well, I'm not much of an author, more a programmer. So I would actually prefer to write blog posts and publish production-ready software on GitHub. But yes, of course, we're trying to write papers and convince people that Bayesian modeling is the way to go.
Well, that's great. Thanks for doing that. And what about you, Tom? Like you told us what you're doing today, like you founded Gradient Matrix and Raycast. So yeah, I'm curious, how's the modeling going there? Like, do you do any Bayesian stuff over there?
Oh, yeah. Basically, with Gradient, it's a lot of different models. So a very common one are doing what are called, choice experiments, right? So the sort of canonical thing is like if you pulled people off on the street and you said, how much are you willing to pay for lane departure assist, a little warning sign in your car if you're drifting out of a lane? And people can't really answer that question. But if you said, here's a Toyota Camry at $25,000 and it has lane departure assist, and here's a Subaru Outback at $22,000 and it doesn't, and you gave them a bunch of choices, people find that task easier to do in a survey. And you can use a type of model called a multinomial logistic regression to unpack sort of why they made the choices they did and what value they placed on specific features. You can imagine in the market research world, figuring out how much people are willing to pay for things is a pretty big thing. So it's a pretty common model that we run, and we run that in Stan. It's nice, though, because not only typically do you want to model what the average willingness to pay is, but you want to model what everybody's willingness to pay is, each person, because you don't care about the average, you care about, maybe the 90th percentile, right? What are the people who are willing to pay a lot for this willing to pay? And so now it's just not a multinomial logistic regression, but it's a hierarchical multinomial logistic regression where you're estimating a willingness to pay for each person that took the survey. And that is very amenable to Bayesian approaches, of course. And so, but not only that, but we do things, other sorts of experimental designs with surveys where we will use Stan to write the code for that. And whereas with Gradient, there's like lots of different things that are project dependent because we do different projects for different clients. with Recast, there is like one big model that I spent all of my time thinking about, which is a big media mix model where companies give us how much they spent on every channel and every day and what their sort of business outcome was, their revenue or their new customer acquisition. And for that model, there is no possibility of doing it other than with a Bayesian approach, in my opinion, because you have very little data. The data that you do have is actually much less signal than you think because the data is not IID. It's a time series. So each new data point is not really giving you all that much information. It's quite overdetermined, the system is, because you have, for any given day, there are like 30 to 40 channels that are changing. The seasons are changing. So there's a lot of different ways for the model to fit the data that you have with the predictors that you have. So you need pretty strong priors. And without strong priors, there'd be no way to actually run the model. And so you need an approach that can take in prior information in order to get something out. So yeah, those are the kinds of things that I'm working on.
That sounds super interesting. I love that. And very good case for Bayesian methods just there. And I'm curious about of course, the multinomial logistic regression. That's something I do a lot too, because I'm mainly for electoral forecasting, for instance, because in France we have more than 2 parties. And yeah, that's useful there, although I'm looking into other structures that I think would be even more helpful. But so then I'm curious, because these models, so for people who don't know, multinomial regression is basically a multidimensional logistic regression, like more than 2 dimensions. And so they are very useful, as you say, but they can be very hard to fit and understand the priors, etc. And something I would love to do, for instance, with polling data is multi-level regression and post-stratification. So MRP, or Mr. P, as Andrew Gelman refers to it. And we talked about that with Lauren Kennedy in episode 34, I think, for people, if they want to refer to that. But I can't do that with the polling data I get because they are all aggregated. You need the disaggregated data. Do you guys get that? Do you guys do that, or?
Oh, yeah. I mean, so we do post-stratification all the time because we often work with quota panels. So with survey panels, there are basically 2 types, right? So there's panels that do quota sampling, right? Where you're like, I have 1,000 respondents I want to get, and population's 50-50, gender, male, female, so I want 500 male, 500 female, and there's 10% of the population is 100 people that have over 200,000 income. And you basically set up a bunch of quotas so that your responses look like the population at large. But you might be getting that sample from a panel that was entirely opt-in, right? So the starting place might be not representative of the population at large. But then there are other panels like NORC, Gallup, Ipsos, Pew, that have probability panels where everybody in the US at least has some probability of being in the panel. And so that's all to say that we often end up with very biased samples demographically. And so you can use things like raking or other weighting methods to give a weight to each individual respondent, which is sometimes more convenient if you're doing things just like creating crosstabs or things like that. But if you wanted to obtain a sort of a point estimate or a point estimate plus some uncertainty around the number of people that are willing to pay X for this product in the US, as you can imagine, pretty important statistic for a lot of our clients, multi-level regression and post-stratification is the way to do it. But there is possible to do marginal post-stratification if all you have are the marginal statistics. I'll send you a paper on that.
Definitely.
So I don't quite understand how it works, but I know it's been done by people that I trust. So that's as far as I can go.
Yeah, you're right. Yeah, that's actually a very good point. And definitely send me that paper. I'm very interested. And I will put that into the show notes also for people interested. And yeah, that's true. I recently heard about that through Eric Ma, actually, who is a fellow PyMC developer. And yeah, indeed, you can do now post-stratification even with aggregated data, which sounds really amazing. But yeah, fascinating. I love that. And I love this kind of data and survey and work. So thanks for sharing that. And these are always challenging, but very interesting stuff. And as you say, since you are trying to estimate kind of the tail of the distribution in a way, so then your model really has to be very custom. Like you are not looking for the mean of the population, you are looking for the behavior of some very specific demographic. So that's where custom modeling is very important. Okay, that's awesome. And a question I always ask and I like to ask is, I'm guessing that you were introduced to Bayesian stats when you were in your math studies, but did they stuck with you at that time or later?
Certainly later. So I don't even think that I took a stats class until business school. I definitely took probability when I was getting my math major, but we had the sort of very traditional stats intro course, right? Like t-tests, ANOVA, that kind of thing, which I promptly sort of forgot. There was a specific marketing class, Marketing 776, which sort of opened my eyes to Bayesian methods, more because it sort of taught us all the different distributions we could be thinking about, right? So, things like the exponential distribution, gamma, negative binomial, Poisson. And I think one of the interesting things in like traditional stats education is that you don't really learn all the different distributions. And in that class, because we were thinking customers, you're thinking about, okay, what products are they going to buy? How frequently are they going to buy? How much are they going to spend? And each of those has a different process associated with it. So in that class, we spent a lot of time thinking about how would the data come to us and what would it look like? And is there a distribution that describes that process? And usually it's not the normal distribution. Usually it's something else, right? If it's the number of times they buy, it could be a count distribution. If it's the time in between they buy something, it's a timing distribution. They all look different. They model different things. And that's when I started to think, generatively, right? Where you're like, I have observed this thing. How did it get to me? And what do I expect it to look like when it arrives? And once you start thinking generatively about how the data set that you have came to be, then I think it's a very short road to being fully indoctrinated into the Bayesian world. But it wasn't until then that I really started to get into it.
Yeah, I'm not surprised, but yeah, it's great to hear. And Michael, what about you actually? When were you introduced to Bayesian stats and did they stuck with you right away or later?
It was during my master's, actually quite at the end of my master's when I did an internship in industry. It was in the data science team at a biotech startup in San Francisco. And a colleague of mine, Robert Ness, some of your listeners may know him. He's also quite active in Bayesian podcasting. He organized this series of meetups, the Bay Area Probabilistic Programming meetups, where he invited famous Bayesian data scientists from the region to give talks. One of them, for example, was Sean Taylor, talking about this new profit thing they had developed. And all of these talks were super interesting, but I was always left with this question mark of how does this really work? I had listened to machine learning lectures before, so optimization and stuff was quite familiar, and also, well, I guess you can't call it generative thinking, but in systems biology, we of course also try to model the biological systems and the processes of these systems. But it wasn't much in terms of probability distributions, and certainly optimization and Bayesian inference with MCMC sampling are quite different and really took a while until it clicked for me. But yeah, so this was my first introduction to Bayesian thinking and Bayesian optimization.
And is that when you started contributing to PyMC and then joining the team?
That was like half a year later. When I came back from this industry internship, I decided to do my master's thesis, something with Bayesian modeling, because I really wanted to learn how this stuff worked. So that's when I started using PyMC3 and also started contributing by fixing a bug here and there, and then implementing the differential evolution metropolis algorithm for PyMC3, because I didn't have gradients in my ODE models that I was building. So I had to find different algorithms. And yeah, DEMCMC was a great choice and still is, the newer version.
Yeah, well, that sounds pretty mathy for someone who doesn't like math, if you ask me, but...
Well, you can do programming without math, and implementing an MCMC algorithm isn't actually that mathy. I mean, you have to get the detailed balance right and stuff, but I didn't have to do any derivations and algebra and stuff like that. So that was my motivation, is always to apply these techniques to get some information out of the data, get some answers, support some decisions. So math and programming are just tools at these points. And with these fancy backends, I can do machine learning and probabilistic programming without actually knowing how to make a differential or an integration by hand.
Yeah, and also I guess with contributing to PyMC was really great for you because it married your passion for software development, programming engineering, and then also being able to, as you say, build models to investigate all these questions, practical questions that you had.
Yes, but still there are huge chunks of the PyMC3 code base where I absolutely have no clue what's going on there.
Yeah, I mean, that's also the beauty of open source, right? Isn't it? It's it doesn't rely on any one person, but it's actually really a common endeavor. And that's also the beauty of it. But that being said,
yeah, definitely.
I guess I speak for the whole PyMC team when saying that we are really glad that you are part of the team and you do so much nice work for the package, especially recently. We'll talk about that at the end of the show.
Well, we can say the same about you.
Yeah, although recently I would have wished to do more. Okay, and now I think is a good time to dive into the meat of this episode, what people came for. Because as I said in the introduction, you both worked a lot on the RT-Live model, which is a Bayesian model to infer the reproductive rate of COVID-19 in the general population. And other links will be in the show notes, of course. Can you tell us how this project came up onto your radar? So maybe first Tom, because chronologically you were the first to be involved.
Sure, yeah. So I don't know exactly when Kevin Systrom wrote this blog post, but the way that I got involved was that Kevin wrote a blog post. Basically, it was I forget exactly what it said, but it said, there's this one number, RT, and it's the number that we should be using to manage the pandemic. And I think if we put ourselves back in the shoes of February, March, April 2020, the vaccine is but a twinkle in the eye of researchers. We have no idea how long it's going to take to get a vaccine. So everybody is sort of thinking we're in this thing for the long haul. We need to figure out a way to live with it, right? Whether that's mass social distancing, something else. And I was really persuaded by the article. I thought, at this point, my mindset is, this could be a 3-4 year thing. Show must go on. How will it go on? And how will we know that we're not exposing ourselves too much to danger? And this one number, which sort of says, is the pandemic getting worse or is it getting better? Which is RT, with 1 being the sort of threshold statistic. Below 1, it's getting better. Above 1, it's getting worse. I thought, wow, that's really cool. But I went into his Jupyter notebook and the math behind it, and I saw that there was, I don't want to call it an error, but there was a problem with the model, which was that he's using data over time to successively estimate this number. But the structure of his model assumed implicitly that that number wasn't changing, right? That with more and more data, you'd get more and more precise estimates of RT, but the model's internal structure did not allow for RT to change from one time step to the next. And so if you look at those graphs, they would always the uncertainty would collapse to sort of a point estimate as you got more and more data. But of course, RT can change over time, right? Because people can social distance, weather can change how the virus transmits, etc. And so there's a connection between that kind of model where there's measurement error, right? And then there's also process error, right? So measurement error is so state-space models happened because people are trying to track objects in space, right? I think that the origin of it was in the space programs in the 50s, and you're shining radar on an object and it's moving, and you get a reading, and you get a reading at the next time step. Well, the reading could change either because of your measurements just having noise or because the thing moved. And state space models are sort of built to sort of balance out those two sources of not error, but changes in your measurements. And there was basically a way to reframe the model that he was using as one of these state space models. And it's one of these things where you recognize it in an instant, but it takes you like 6 hours to work out the math or something like that. You're like, I know it's true. I know it's right. I just don't know how to show that it's right. I don't know if that ever happens to y'all, but it definitely happens to me. And so I basically wrote him an email saying, hey, I love what you're doing. This is extremely cool, but I think you can improve it by making this assumption. Here's how to reframe it as this.
So at that point, you had figured out the 6 hours of hell math that you were talking about were behind you, right?
Yeah, right. Yeah, at that point, I had coded up a proof of concept and shown here's my estimate and yours, and they're very similar, except mine's, you still have some uncertainty at the end, that sort of thing.
Yeah, and you didn't know Kevin at that point. Yeah, okay.
No, not at all. Never met him, never talked to him, no mutual friends, nothing. And so he emailed back being like, yeah, I think this is right. I forget exactly what happened, but over say a week later, we started to do pair working sessions. We'd get on a Zoom and we'd either be writing code or looking at an academic paper. And then basically from there was so much scrutiny on the model. We had people from the Fred Hutchinson Center, people from the Rockefeller Institute emailing with critiques of how we were computing RT. And some of them were really, really good. A lot of them were just nitpicky, and you would make the change and you'd see okay, the estimate changed by 0.1%, fine. But over time, we basically kept on rethinking how we were building the model. And because there is no one way to calculate RT, there are hundreds of papers, all with different assumptions, all with different approximations. Because the underlying model that is sort of generally accepted is a differential equations model. And I don't know if PyMC3 can, but Stan has an ODE solver, but these things have historically been very hard to estimate with solving the differential equations. So people have different approximations of it, and different approximations perform well in different circumstances.
And the model was in Stan at the time?
No. It was always in PyMC3. I wrote some versions of it in Stan just to gut check things. But at any rate, eventually, after many iterations, Kevin came across this blog post that referenced a couple different papers that's in the show notes. So if readers are interested, they can take a look. That just said, why are we approximating anything? Why are we solving differential equations? Why aren't we just simulating an outbreak, right? And the way that the SEIR model works is that there are people that are susceptible, they get exposed to the virus. That means they are infected but not infectious. Then they become infectious, they can spread it to other people, and then they've recovered. And so each of the periods where they are exposed but not infectious yet, and they are infectious and giving it to other people and then stop, those have different timing distributions associated with them. We just figured, and this was Kevin's insight, that let's just simulate an outbreak according to these parameters, right? There's a certain number of people infected today. Some of them are infectious, some of them are not. The ones that are infectious, they're at this point in the density curve throughout the life cycle of their infectiousness. And then RT is 2. And so we're going to assume they give so many people, they infect so many people today according to these different timing distributions and what RT is. And it's the beauty of the sort of the Bayesian way of doing things is that if you just sort of simulate an outbreak inside of PyMC3, you can then estimate the hidden parameters of the outbreak. And in this particular case, RT was the main one that was determining how fast or how slowly it would grow. And then that just made everything sort of clicked into place. Once we got onto that version of the model, the progress just sped up exponentially. So the life cycle was, there was this initial stab that Kevin put together that was great, but had a couple of flaws. I proposed this improvement that made it a little bit better. And then we sort of got really educated in the industry, talked to a lot of outside experts, and then eventually just went with a purely generative approach, which was Kevin's idea, which is the way that the model ended up working for RT Live. And I assume it's the core of the RT Live Global, although I'm excited to hear what has changed since I rolled off the project. But that's sort of in a nutshell, what the evolution looked like.
Yeah, well, thanks a lot for this very detailed and yet still high-level narrative arc of the model and all the process. You basically answered all my main questions I had about the model. So thanks a lot for doing my job for me. And yeah, as you say, this model is such a wonderful example of Bayesian generative modeling. This is really, really great to read. And it's funny to think that maybe it could not have happened because, Kevin Systrom is kind of a high-profile person. So I'm guessing that he doesn't read all the emails he gets. And so I figure that your email could have easily ended up in a spam folder somewhere and just be there for, I don't know, it's 30 days before it's automatically deleted. So yeah, a bit of chance here that I love, a bit of randomness.
Yeah, indeed. I fully did not expect him to respond. I just figured I have to send it out and then.
Yeah. I love that. It's a great story. And so Michael, before we get into a bit more detail of the models, and maybe you can tell us the main knobs of the model and maybe how that evolved from the original version. But first, tell us how you got involved with the project.
Yeah, I think it was then essentially around the same time, because it was March 21st when Thomas Wicki posted the link to Kevin's blog post on the PyMC Slack. And he also got into touch with Kevin. If I remember correctly, Kevin and you, Thomas, you were having problems with productionizing the model with PyMC3 and specifically with the workflow automation framework that you were using at the time. And then a few people from the PyMC team jumped onto the other Slack channel and started helping out. And that was also when I started joining in on some Zoom calls and looking for ways how to contribute, which was really hard because I think one has to say and point out that Kevin really spent multiple weeks of 12 hours a day working on this model and running it. So the website that had launched quite early was updated every day. And you were working with this, let's call it version 1 of the model, where the modeling was split into 2 stages of a pipeline, where first the test counts were incorporated into the model to describe this one time series, and then the second part tried to model that one. But this switch to the generative model was really a big deal because it made sort of collapse these 2 steps into one. And this is actually still the model that we are using for RT Live Global. Yeah, so very briefly, that was my perspective on how the model evolved. I wasn't very much into the details for a long time there because...
Yeah, but I have fond memories of these Zoom calls. I remember it was early spring 2020, and it was very funny to really, we were, I don't know, maybe 10 or even more sometimes of the PyMC devs plus Tom plus Kevin on these Zoom calls, and diving hard and deep into the model, and it was ideas were flowing. It was really, really amazing. And I have fond memories of that, although it was very challenging, as you said, because you had some people there who were quite specialized in epidemiology, like Chris Fonsbeck, for instance, Adrian Zabel.
And if there's somebody who spends 12 hours a day improving a model, then it's really, really hard to keep up with all those changes. Yeah, so I think I really started contributing when I noticed that this way how the model was productionized at the time wasn't really scaling. And Kevin had massive amounts of work because he spent like 2 hours every day just to run all these MCMCs. Because from day one, the model was running for almost all the states in the US. It was like more than 50 regions. And for every region, this model runs for like half an hour, 1 hour. Depends on the version of the model, but it really runs for so long that you have to parallelize all these MCMCs. And it turned out that this...
And invariably something would break, because like Alabama changed its number last week, and or like Mississippi or Montana or whomever, they didn't report their numbers, or they batched all the numbers from a week onto one day or something like that. So there's always some kind of data issue because you got 50 states. And so that could cause divergences, or it could cause like huge changes in the RT curve from one day to the next. So it wasn't just the time, it was also like invariably something would break and it would have to be investigated. So, poor Kevin, he was airflow.
Yeah, I think it's worth to...
It was Kevin airflow.
Yeah, I think it's worth to do an back on the envelope calculation here, because if you have 50 states or 50 regions, because it's not actually states, it's regions that are being modeled, and you have all those 50 ones every day, and then let's say 10% of the regions run into some trouble because of data issues, because of sampling issues with the MCMC, because of memory issues with the runners, whatever, then you have 5 regions every day that you have to look into. And this happens at some point in the morning. And as long as you don't look into this, you can't update the website. And the way how the model was productionized at the beginning was that Kevin had to actually resample and rerun all the regions after fixing an issue in one of them. And because this rerunning took like 2 hours, this was actually a massive pain. So I saw this opportunity there to contribute by helping them to switch to an Airflow cluster. So for those who don't know it, Airflow is a workflow orchestration engine that is really great at parallelizing data workflows across multiple machines. And just like 2 months before, my colleague Laura Helleges and we had set up an Airflow cluster here at our institute for running own models. And then this pandemic came around, and then this RT Live project showed up on the radar, and it was really just a very good natural fit to help them, specifically help Mike Krieger, who then set up this Airflow cluster and migrated this productionized RT Live model onto the Airflow cluster. And this really reduced this time of manually spending 2 hours, 2 Kevin hours a day into running the model. This went down to like 15 minutes or so. And we had like automated Slack messages that would just point out the like 2 or 3 regions that were failing with some divergences or data issues or really unrealistic changes compared to the day before.
Yeah, so folks, as you can see, modeling is not only statistics. It can be like a huge part of a modeling workflow can be, okay, how do I productionize that and make sure that we can run that? And not only run that, like now that there is this cluster, you are more able to, if you want, like improve the model because you don't have these back and forth and you have to wait 2 hours for the model to run and then get back to it and improve it. So yeah, I mean, that's a great example. And out of that, you built the RT Live global website, right? Where people can compare the RT number, but also the infection rates, etc., for different countries that I put in the show notes, of course.
Yes. So after running the model for the United States for a few weeks, of course, we wanted to run the same model for Germany. So my colleague and I, we sat down and said, okay, let's try to figure out how we can migrate and globalize this model such that it doesn't only apply to the US, but it can apply to Germany. And there were like multiple problems or multiple challenges. So challenge number 1, the model wasn't programmed to be applied to any other country. So first we had to like refactor huge chunks of the modeling code to be independent of US states and instead use something like ISO country codes and region codes. We also had to figure out how we can incorporate the data that we got for Germany, which was very limited. Like our data source is actually at the Robert Koch Institute, where we have to write emails, and then we get a non-public data set that we use for Germany. Because in contrast to the US, the numbers of tests performed per day per region is not publicly available in Germany. Long story short, we added a profit model to our data pipeline that takes these daily numbers of total tests performed per region. It's like this zigzag curve, and then this profit model makes a prediction, and then we use this prediction for the RT Live model. And so we did this for Germany, and you can take a look at github.com, RT COVID Live /RT Live minus global. The code is actually written such that you can incorporate other countries. We now have like a collection of countries, and Alex, you implemented the data loaders for France, for example, which, by the way, has really, really great data quality. I would love to have such data quality for Germany. And since we launched it in, I think, August last year, this Airflow cluster has sampled the model in more than 40,000 sampling tasks, each one of them with 6 MCMC chains. So we have a few hundred gigabytes of RV's inference data objects with the MCMC traces. And as you can guess from these numbers, it's super important that there are like convergence checks and all these exporting this. Like all of this has to be automated. That's absolutely not scalable if you do the math without.
Yeah, that's really a great project. And thanks for doing that for us, and thanks to Laura to contribute to that. It's really something great to have out there. And so definitely I encourage people to take a look at the webpage and at the GitHub.
And for those interested in how you can productionize PyMC3 models with Airflow, Mike Krieger also wrote a blog post about it. I also added the links here to the show notes.
Perfect. Yeah, we need that. We need that in the show notes. Thanks.
Let me show you how to be a good Bayesian.
Hey folks, as I told you at the beginning, this episode is brought to you by PepperPie, the reference manager you actually want to use. You can cite in BibTeX and search inside databases right from Microsoft Word or Google Docs. There is no way to cite faster. You can read, annotate, and even collaborate with your co-authors in the modern web app or in the iOS and Android apps, which automatically sync your library to all your devices. As a listener of this podcast, you get all these features for only $29 a year. That's a 20% discount with the special promo code GoodBayesian21. So go ahead and check out pepperpie.com before December 31st, 2021. So that was the software engineering part of the model, which again was super important for this model. And then let's get back a bit more into the statistics details. Maybe let's get back to Tom for that. And Michael, if anything changed in the RT Live global model, feel free to jump in. But basically, Tom, can you tell us a bit more about the generative story of the model, and mainly what are the main knobs or hidden parameters, that the model is interacting with and trying to infer to get to RT?
Yeah, definitely. So basically, I think I can walk through the whole thing from memory, but there may be some errors here. I may have to consult the code as well as the rest of the audience. But so it starts with a seed.
I will raise my hand when you get something.
Okay, great. Thank you.
Get something wrong, as far as I can tell.
So it starts with the initial seed of people that are infected. And then one of the first, well, they all get modeled simultaneously, but temporally, we can think of it as the first thing is just this initial population of people that have COVID. And then there are two timing distributions that matter. So one is, so in the SEIR model, as I was talking about before, you get infected, and there is a period where you are infected but not infectious, and this is called the incubation period. So if I receive the virus from one person, there's some time before I can give it to the second person. And that, I think, is roughly 3 days, if I recall correctly, but there's some distribution, right? So it's not 3 days for everybody, it's 3 days on average. And so there's this timing distribution of the incubation period. And then there's a second distribution, which is the infectiousness period, the period over which you can give the virus to somebody else. And again, this is not a single number for everybody, but it is a curve. Like there are a couple days or there's a week over which if I had the virus, I could give it to somebody else. And not only that, but there are some days where I'd be more likely to give it to somebody else than other days, even if I could on either day. When you take these distributions and you sort of fold them together, you get a convolution of the period over which a single person could infect somebody else. And so what the model does is it takes this initial seed at some point, and then it time step by time step takes the number of people infected on that day, and then it convolves this according to the two distributions I mentioned before.
Yeah, so infection, like incubation time, and then infection time.
Right. So it basically says, okay, somebody was infected today. What is RT today? It's 2. Okay, so this person is going to infect 2 people. And then when are they going to infect 2 people? And then it's those 2 timing distributions I talked about before that determines when the 2 people will get infected. And so we have this basically a big loop that's in Theano. So it's totally inscrutable to me. And somebody named Junpeng Lao wrote it, and it works. But it was like a brilliant piece of software engineering because Kevin and I could not figure it out, but he did it, that does that, right? That basically time step by time step. How many people were infected today? What is RT today? Okay, that's the total number of people that they will infect. And when will that happen? It'll happen according to these distributions. And then so we add like a new layer of people being infected into the future. And so it does that.
Yeah, as Michael pointed out. Yeah, so like the technical names for these 2 distributions, do you want to tell them, Michael?
Yeah, so one of them is technically called the generation time. And
so it's the incubation period? Yeah.
It's not exactly the incubation period. And I don't want to be wrong on the definition here. So I will point to one of the show notes, which is a really great resource on terminology in this epidemiological modeling. Yeah, so generation time is one of these distributions, and the other one is the delay distribution, which I'm sure you will come to in a moment.
Right. I wasn't going to, but I'm so glad you reminded me because that's another thing. Right. So everything that I've described so far is just to the infections, right? So all I have described is this curve of infections out there somewhere, but we don't observe infections ever. We observe positive tests. And so there's this other sort of thing that you have to think about, which is how do infections show up as positive tests? And then how do those tests get reported? So there is another timing distribution, a third one, which is delay between when you get an infection and when you get a positive test. And by the way, for each of these different timing distributions, these aren't things that we modeled. We relied on other efforts by academics and published reports on what these intervals were. And so those are sort of coded into the model. They're not things that we tried to estimate. So there's this yet another timing distribution, which is from infection to positive test that we had to incorporate. And then the other thing that we had to incorporate was the sort of testing density, right? So I think we're testing something like 30 times as many people as we were a year ago, right? So all else equal, you will certainly get more positive tests if you're testing orders of magnitude more people. And this was especially important because at that point in the pandemic, testing was one of the big things that the federal government and everybody was focused on, was increasing the number of tests. And so in some states, it was ramping pretty aggressively. And so we made an assumption in the model that the number of positive tests that would be reported was locally linear with the number of tests done, right? So if basically the model assumed that on a given day, if you observed 100 positive tests and you did 1,000 tests, had you done 2,000 tests, you would have gotten 200 positive tests. Now, we did a bunch of sensitivity analyses to figure out how much this assumption was robust to different possible realities of the testing regime. And it turned out that since the period of COVID, all of these timing distributions laid on each other is about a 2-week thing, right? The incubation period is a couple of days. The period over which you are infectious is, a week or two, maybe 10 days. And then the delay distribution between when you get an infection and you get a positive test is maybe a week, maybe less. Certainly less now than it was then. We're talking about a 2-week thing, that there's this number out there that is, what is the fraction of actual infections that are getting reported? And we never know that number. And that's the number that we care about moving up or down. And we did a bunch of sensitivity analyses to figure out how much our reported number was sensitive to that changing very quickly. And it turned out that the locally linear assumption that I just mentioned was pretty okay, because if the dynamics of the number of people who were actually positive, testing positive, didn't change that fast over, say, a 2-week period, which we thought was reasonable, that it didn't matter all that much. But that was the one thing that we were super sensitive to, was we don't actually observe infections, we observe positive tests, right? And the other thing just quickly to mention is that RT is like a scale-free number, which is a good thing and a bad thing. And the good thing is that you'll get the same exact RT curve if you divide all of the numbers by 1,000 or multiply them by 1,000. So it only sort of measures relative rate of change, not the absolute number. So the fact that we were sort of estimating the number of infections up to a constant multiplier, and that was fine for RT's purposes.
This assumption that you mentioned, I think this is still one of the main differences between the RT-Live method and a lot of other methods for calculating RT.
So which one, Michael? Can you remind listeners?
This assumption that the numbers of confirmed cases scale locally linear with the numbers of tests performed.
Yeah, so just to recap a bit before you go on, that means we have 4 things we just talked about that we have to care about, which is I get infected, the time between getting in the incubation period, basically, then the time between being infected and becoming infectious, then the time during which I am infectious, and then the time where I am infected and I get a test, a positive test. And then you have to add to that another layer, which is, okay, we have to correct for the scaling in the number of tests. Was my summary accurate? Did I forget something or add something?
I think you double counted the incubation period.
Yeah, I think so too.
If I heard correctly, but I'll just recap it quickly. So it's, you get infected, and then there's a delay between when you're infected and infectious, right? And that could take a variable amount of time. Then you're infectious for a certain amount of time. And then there's a delay between when you are infected and when you'll get a positive test will get reported. So it's those 3 things: incubation, infectiousness period, and then time until you get a positive test.
Yeah. And then you have to adjust for the scaling in the number of tests.
Yeah, exactly.
Okay. Yeah, makes sense. I did count infectiousness 2 times. So good thing you corrected me. Yeah, Michael, so the floor is yours again.
So maybe for those who are more visual people, at rtlive.de/global, we have a lot of visualizations that actually plot quite a few variables that are extracted from the internals of the model. So for example, if you click one of the thumbnails, then you get a big details plot with 4 subplots, and it has multiple density bands. In the topmost plot, for those people who are just like opening this up on their phones. The topmost plot has this red density band, which describes the numbers of infections per day, with the time axis being like the day of infection. And then this first time series, this is smeared sort of into this green time series by the delay between infection time and when the test results arrive. But then we don't really observe this green time series that has this, like, it has a very similar shape. It's just like smeared to the future by a few days. But we can't observe this because it scales with the numbers of tests performed. And then if we apply this, then we get to a variable that we can actually compare to the observations we made.
Yeah, I highly encourage listeners to go to that page and see that for themselves. It will be in the show notes.
I think something we should not forget is, how does the model even describe RT? I think that's like the core of the generative nature of this model, that RT is really at the beginning of this generative process. Tom mentioned this seed number of initial people infected, and there's also a seed number for the RT value at time step 0, but then the model describes RT as a Gaussian random walk, where basically the time series is just a huge vector with like one element per day, and RT is allowed to drift up and down. And the model estimates this RT by like assuming a certain vector for these values and then putting this into the generative part of the model that simulates the outbreak. And the MCMC is really stepping on the values of this RT vector. So this is what we get out from the MCMC in the end.
Yeah, just talking again about this model, I'm still amazed. I love it how all the different parts, get together, and really the generative nature of these. Also the software engineering challenge that you mentioned, and also like the melting pot that it is, because like it's really using prior scientific knowledge, as Tom said, like this generation time and delay distribution, like they are not estimated by the model. They are taken from academic papers and they are put into the model. They are used by the Bayesian model. So in a way, these are priors. And yeah, so like you have this use of scientific knowledge, this generative structure, and then of course this uncertainty estimation that I love. And of course, as Michael said, like one part of the model is using Prophet for the test counts, and then it's the MCMC for the RT number is done by PyMC3. So even in the software it's using because Prophet is based on Stan, of course. Like this is great. It's just so diverse. I love that.
What really intrigues me about this model is I think it makes strong assumptions in some places and weak assumptions in other places. And I think it makes the weak assumptions or the non-informative prior assumptions in just the right places. And it's actually amazing that this model can be applied to so many countries. Of course, the more you dig into the details, the more you find out that the model is actually wrong. All the models are wrong. Everybody knows this, but this model makes simplifications that are justified and derived from the underlying SEIR model by basically making these time-step discretizations. Then it incorporates this smearing of these time series because of these generation time distributions and delay distributions, where other methods, for example, would just take point estimates for the generation time instead of distributions. But then this underlying assumption that RT is this value that sort of drifts over time, and like with equal probability, it's drifting up and down. It doesn't make any strong assumptions. And in the end, you can basically fit this descriptive model to the historic data of many different countries, as long as the data quality is correct, of course. And this is, I think, one of the contributors to the success of applying these models to, I think, almost 200 different regions by now, without actually making any adaptations that are country specific, because we don't have the tuning knobs where we could say, okay, here we make a country specific adaptation, because for a lot of these knobs, there is no data for how should we change the generation time distribution, for example, when applying the model to the US or to France. We don't know how to change it. And I think this makes the assumption that we have quite good, because if we don't know if we should like turn the knob to the left or to the right, then leaving it just where it is quite justifiable.
Yeah, definitely. Okay, we're getting short on time there, and I do want to talk about PyMC developments. So let's wrap up on this great model. Maybe I ask you just a couple more questions, but try to answer quickly if you can. Tom, I'm curious, what's the main challenge? What would you say was the main challenge for you during this whole modeling process that you encountered?
I mean, it was just so much time, if I'm being totally honest. I was sort of in awe of how much time Kevin could just devote to one thing. Like his ability to sit in a chair and just work on something for hours at a time is kind of unmatched in my experience. And keeping up with him and, staying up late on, random nights, and also trying to run gradient, run recast was tough. I mean, the fact that it was super locked down in New York and there was nothing else to do was pretty helpful. But that was the main challenge, just keeping it all together and finding the time to devote to it. Because we present this really sort of clean picture of how the model works today, but it involved so much research into epidemiology and communication with experts before we could get to a place where we knew all the different time convolutions we needed to include. And so that was definitely the biggest challenge for sure.
Yeah, it's a lot of trial and error. And that's a point I often highlight in this podcast. You don't have to have a perfect model from the onset. Don't be intimidated by that. The models you see in blog posts and so on, it's the last iteration of a model that didn't work before.
Yeah, you're seeing the edited version, the highlight reel, not the cutting room floor.
Exactly. And yeah, Michael, maybe I'm guessing it was the software engineering stuff, but I don't know, I could be wrong. What was the main challenge for you?
Yeah, I mean, sure, getting all the different tasks, like the working on my PhD projects and all of that under the same hood, of course. When it comes to the model, I would say refactoring a model that was really specialized to the US into this globalized version, while at the same time implementing visualization tasks that were sort of independent of the country. There are these technical details for the German website, we wanted to have plots with German labels and German date formatting. And it's actually super hard to make plots with German date formatting and English date formatting on the very same Docker container. So there were a lot of technical challenges like this one. Then, of course, communication and getting this model up to a website that actually people could visit, because we didn't want to spend all these compute resources on something that nobody was actually looking at. So this was really a challenge, yeah.
I can testify to that. I saw you working in that. And maybe last question on that, do you see any, if you had the time today, is there something you'd like to improve on the model, or are you pretty happy with where it is right now?
Well, if I could write a wish list just from the modeling perspective, I would say being able to fine-tune the generation time and delay distribution, also the delay between infection and when the infectiousness period starts. This is not actually a model variable, it's just the constant right now. But also, we have this profit model that predicts this time series of daily performed tests. But then we just take the point estimate of this time series and feed it into the RT-Live model. But the profit model is already a Bayesian model. So theoretically, of course, this time series and the uncertainty about predicting the daily performed test, this could theoretically be incorporated into the full model, and also right now the model makes the assumption that the standard deviation of the Gaussian random walk, so the possible rate of drift for the RT value, that this is a constant, and we don't estimate it because, it turns out that
Oh, yeah. This is giving me like PTSD. I remember.
Yeah, so it was basically a trial and error to find value for this. And it would be great to estimate this. One alternative could be to substitute the Gaussian random walk with a student T random walk, because this way the random walk would get the ability to have like switch points where there could be a sudden jump in the RT value because maybe a policy changed and people started taking off their masks. So this would be great. And I did a few experiments with this, but if there is something that drives up the compute time of this model from like half an hour to 60 minutes, and then it doubles the compute time to 2 hours, and in some cases leads to divergences, then this is not something that we can deploy for almost 200 regions. So maybe there are some tricks that one can do in the implementation to make this more efficient, but this would definitely be a great thing to look into.
Awesome. Well, thanks again for this deep dive. That's really fascinating. I love that. Before we close up the show, though, I'd like to ask you one question about the future of PyMC3, Michael, because we are lucky enough to have you with us and you work a lot on the coming brand new V4 of PyMC. So what can you tell us about that? What are the current developments and where is the project headed basically at a high level?
Yeah, so I mean, I'm definitely not the one who puts most of the work into this.
Yeah, as always, it's a team effort.
But I can tell you that we are just around the corner of merging the V4 branch into the master branch of PyMC3. So the next big version will actually be just a major version bump for the PyMC3 package, because most of the modeling API will actually stay the same. It's a huge refactoring of the internal workings of PyMC3 and sort of the paradigm, how model variables are constructed and evaluated has changed entirely. But for like 90% of the use cases, we can keep the user-facing API identical. And we will actually use this major bump in the version to make some breaking changes that make the project more maintainable. And for example, we will switch to returning inference data objects by default, because we believe that with these RVs-based inference data objects, you can get to like more robust modeling workflows. So yeah, we would like to improve the user experience, raise informative errors, have a more coherent shape dimensionality API, things like that.
Yeah, and what would you say will be the main value added for users? Like, how will it make their modeling lives easier? Like, what are the main points?
I would say the user base will benefit greatly from PyMC3 being more maintainable for the developer team and easier to contribute to.
I think there are also some shape magic right now, like all the posterior, like the forward sampling should be much easier now, and basically like just shape handling in general, right?
Yeah, the sampling will be easier. And one of the big cool new things is that we are switching the backend from Theano to Azara. And Azara has lately gotten a lot of really cool upgrades that allow you to, for example, compile the computation graph with JAX or even with Numba, which in some cases can give you like really big speedups for the models. So that's definitely one of the biggest changes, that our backend is changing from Theano to Azara, which is basically the really big refactoring of Theano that makes it more maintainable. And I think that's going to be great.
Yeah, I mean, better shape handling. I'm not saying automatic because I'm not deep enough into that, but that's what I understood. But at least much better shape handling and massive speedups. I mean, what's not to like, right?
Of course, it really depends on the use case, as always. But we definitely have a lot of improvements around the corner. So.
Oh, yeah. I mean, I'm so excited for this new version. Like, I can't wait to try it out even more and also see what people do with that and the feedback we get. That's always super useful. Okay, guys. Well, I think we can call that a show that was a pretty dense session. Thanks for sticking around that long. Of course, before you go, you know the drill. I'm going to ask you the 2 questions I ask every guest at the end of the show. The first one is, if you had unlimited time and resources, which problem would you try to solve? Tom, you want to start?
Oh, man. If I had unlimited time and resources, what problem would I want to solve? Alex, I didn't know that this was the question that you asked everybody. So I am I would say basically the problem that I'm solving right now with Recast, which is when you spend money on marketing, what does it do for you? But that is the absolute lamest possible answer that anyone could ever give you.
If you want, we can ask Michael, and then you get a few seconds to.
Oh, I know. I have an answer. So
You see?
Right now, computers are really good at pattern recognition, right? Almost all of artificial intelligence is models that take input and output pairs, right? Or make new data that looks like this existing data. But what computers are really not great at is just like abstract reasoning, right? Laying out a problem and solving it with common sense, but people are really good at that. And one of the things that we know is that what we do in our brains is nothing different than a Turing machine or lambda calculus. It's just computation. So there's no reason that we shouldn't be able to imbue computation with what we think of as common sense, even though it just does not exist in any algorithm that at least I'm aware of. I mean, you can program a logic program. You can use like Prolog or other sorts of logical programming languages to do it. But general reasoning, it does not seem to be something that we can do today. And I think that would be pretty valuable. So I would work on that. Or fission. That or fission. One of the two.
Yeah, definitely hard endeavor.
Yeah, pretty hard. Yeah, exactly.
Yeah, both hard problems. But I mean, that's the question. Yeah. Michael, what about you?
Yeah, I guess my answer is quite specific on your first question. I would work on upscaling microbial CO2 fixation. Like, we have this massive problem in our atmosphere of emitting too much CO2, and I think it's quite clear we don't only have to stop emitting it, we also have to get it back out. And biology is really good at this, and there are some research projects working on fixating CO2 with engineered microbes, basically. And I think if we could scale this up to like big technical CO2 fixation facilities, that would be great. So that's what I would work on.
Yeah, great answer. I can see that. Yeah, you really thought about that. That's great. Okay, second question now. If you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be? Tom, do you have an idea?
Yeah, no, I mean, this was a lot easier. So I think I really love Steven Pinker. He's written books on The Language Instinct, I think was his first big popular science book, but also on like the history of violence over time and things like that. He's become a more controversial thinker in recent years, but I find him fascinating, and I think he'd be a very good person to like have dinner and drinks with. So he would be my answer.
Perfect. Does he live in New York?
I think he lives in Boston because I think he teaches at Harvard. So not too far. I could go hang out with him.
Oh, that's pretty close. Yeah, I'm guessing he listens to LBS. I mean, he'll basically knock on your door.
I mean, he's a very, widely read person and dabbles in a lot of different intellectual cultures. So I wouldn't be surprised, actually.
Yeah. I would be honored. And Michael, what about you?
Yeah, my answer to this question is related to my previous answer on the first question. So I would have dinner with Aaron Bar-Even. He was a group leader at the Max Planck Institute for Molecular Plant Physiology and worked on exactly this problem of CO2 fixation. So he was a very promising scientist, but unfortunately died at a really young age last year. So there was a huge shock to the CO2 fixation community, let's say. And yeah, but he was a very enthusiastic researcher, biotechnologist, and metabolic engineer. So yeah, I would like to meet him again and talk about this research stuff.
Yeah. I love how thorough your answers were. Thanks. Okay, guys, thanks a lot. Modeling COVID-19 is a very complicated endeavor, as we saw, but I have to say it's really scientifically fascinating. I want to personally thank you both for your tremendous work on this very useful project. Really a project for the common good, and also thank all the other people who participated in this adventure, Kevin Systrom, Laura, your coworker, Michael, and also the PyMC team, as you said, Junpeng Lao, who did his classic Theanoscan magic. So, I mean, it was really a common project that was fascinating to be part of. As usual, I put resources and a link to your websites in the show notes for those who want to dig deeper and really look at the show notes. They're really great for this episode. I have them in front of me right now. Thank you again, Tom and Michael, for taking the time and being on this show.
Thank you for having me, or having us, rather.
Yeah, thanks for this great discussion about epidemiological modeling.
Yeah. Really awesome. And next time there is a big global pandemic, you are, of course, welcome again on the podcast.
Well, I don't want to say I never want to see you again. Under those circumstances.
Not on the podcast.
Yeah. All right. Thank you very much.
Okay, guys. Thanks. See you.
Take care.
This episode was brought to you by PepperPie. PepperPie is the reference manager you actually want to use. It integrates seamlessly with Google Docs and Microsoft Word and allows for live collaboration. Learn more at pepperpie.com and enter the promo code GoodBayesian21 at checkout for 20% discount. This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher or on Podchaser, and visit learnbayesstats.com for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, with MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thanks so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.